Thank you for tuning into Your Inner Genius with Professor Pete. We're going to be looking at some selected works in Calculus 2, and we're going to start off with the area of a region between two curves. So let's take a look at what we're trying to figure out here. Basically, we have two functions. We have an f of x, and we have a g of x. Okay. And what we're trying to find out is what the area between these two are. Okay. So let's take a kind of a gander and see how we're going to do this. Now, if you'll just kind of play along with me, then I'm able to draw perfectly, and that my f of x always looks the same, and my g of x always looks the same for this example right here. Just kind of play along. So this is the same f of x. Alrighty. So if we had this on its own, we would know that this area right here, if we were to figure out the area, that would be, this area right here. That's what we would be figuring out. Okay. Now with our g of x, say this is the same as our g of x. Figuring out the area, that would be whatever is below the g of x right there. So what we're trying to find out is what the f of x is minus what that g of x is, kind of like this right here. Okay, that's because if we took out the g of x from here, if we took out that part right there, that's right here, we would come up with the area that we're trying to come up with. Okay, that's just kind of a basic idea of where we're going with this. So how do we do this? Well, we need a tool, and the tool that we use is a theorem. It's basically called the area of a region between two curves. Okay. Now in order for this theorem to work, there have to be two things that are true. Okay. First thing that has to be true is f of x. You have two functions, f of x and g of x. And within a region from A to B, they have to be continuous. Okay, what do we mean when we say something has to be continuous? I'm just going to kind of give you the concept that's easy to understand of what continuous means. I'm not necessarily going to give you the book definition, the math definition of it. I'm just going to give you kind of an idea. A continuous graph is one that just flows nice and smoothly. It goes down, it goes up, it curves, it goes diagonally, it goes wherever it wants to do as long as it does it smooth and evenly. It doesn't go backwards, it doesn't have sharp corners, it doesn't do anything zigzaggy or anything like that. That is not continuous. Okay, so if you can see the difference there, right before here it's continuous, after here it's no longer continuous. Okay, so that's basically what we need. Now the other thing that we need to be true is that we need f of x to always be greater than or equal to g of x for all x in A to B. What does that mean? That means that within the range where we're looking, f of x, if we're looking at it horizontally, f of x always, or vertically, or f of x always has to be above g of x. Or if we're looking at it vertically, f of x always has to be to the right of g of x. Okay, so like this is our f of x, this is our g of x, where they meet, the intersections right here are our beginning and end of our range, or a and b. We can see that our f of x, which is this one right here, is always greater than our g of x. If we're looking at it the other way, we have an f of x, we have a g of x. We see that our f of x is always to the right of our g of x. So it's always greater than. Those are the two things that we need to be true. Now if these two things are true, then we can apply our theorem, which basically says that the area is going to be the integral from A to B of f of x minus g of x dx. Okay, you see we have our f of x and our g of x back again, just like we were taking a look at before. When we had these two graphs, we had the f of x and we had a g of x. And we had f of x, which was this area all the way down here, right? And we had the area of our g of x, which was this area right in here. When we took away that g of x from the f of x, we came up with this area. Well, that's exactly what we have applied right here. So now what are we talking about? What are we basically saying, sort of like in English speak, when we take a look right here? Okay, when the fundamental theorem of calculus, what it all kind of boils down to is you have this graph. We're just going to look at it for one function. Okay, we have this graph here, with this function f of x, and it mostly applies to the area. Okay. If we are able to take, it's really hard to figure out because this, is kind of curvy. It's kind of crazy. It's easier, like I say, if f of x was a straight line, it's real easy to find out, the area below a straight line, that type of thing. But if it was curvy, what do? Well, we take what we know, and what we know is for straight lines. So with the integral, which comes from the limit, and we can look at that in earlier videos if you'd like to take a look at. What we want to do is we want to take short little line segments, and these line segments are so small that you can't even see them. I mean, they're so small that they are actually straight line segments. Okay, so we have this straight line segment, and we make a little rectangle, and this rectangle is really, really tiny, and we make each one of these little line segments the top of a rectangle. Okay, so just imagine that. Each one of these is a little itty-bitty rectangle. Now, as x changes, we call this our d of x. That's where that comes from. What that d of x basically means is the change in x. Okay, so that's what that means. That means as x goes this way, the a to b are our endpoints. So we have an a here and some endpoint over here, b. The integral takes each one of these little rectangles and basically just adds them together. So that's really the concept of what this is doing here. This is taking this f of x and this g of x, and it's making these little itty bitty rectangles that are so thin. They are just wafer thin, where you can't even see them. And so that the top is a straight line and the bottom is a straight line, so that we are able to apply our, the things that we know about, like the area of a region below a straight line. We know how to do that, and so we're able to apply that with that concept using the integral. So that's basically what we're doing. I'm just trying to give you kind of a concept of where we are and what we're trying to do. So let's put this into a real-life application so we can see this happen. And we want to start off real basic. We want this to be as easy as we can so we can get this concept. So what are two functions that are just going to be the easiest things we can do? Let's pick two straight lines. How about that? I love it. Let's say the first one is f of x is equal to 4. What do we mean when we say something like this? That means that for any value of x that we plug in to f of x, we're always going to get a 4, and that is the straight line f of x equals 4. And our other straight line, we're going to pick g of x equals 2. Okay, that basically means that for any value of x that we plug in, we're always going to get the value 2. Okay, now you can see these are obviously continuous. Assuming these are straight lines, they're continuous. F of x is always above g of x, so we're good there. Now these kind of go off to infinity both ways, so we need a region. We're just going to go ahead and pick a region. We're going to pick a region from A to B, and we're going to say A is 1. We're going to say B is 3. Okay. Now we're going to get our little line segments like we know. Okay, and this is at 2, and that's over here at 4. Okay, so what we want to know is we want to know what this area is right here. Okay, so we already know that these two functions fit within our criteria, f of x and g of x. They're both continuous. F of x is always greater than g of x within this region. So we can apply our tool, which is integral from a to b of f of x minus g of x d of x is equal to the area. What does this interpolate into? From 1, which is our a, to b, which is our 3, f of x, which is 4, minus g of x, which is 2 dx. Okay, that gives us 1 to 3, 2 dx, which gives us 2x evaluated from 1 to 3, which gives us 6 minus 2, which is equal to 4. Does this make any sense? Let's take a look at it. Let's write out our graphs again here. We got f of x, and we got g of x. This is equal to 2. This one was equal to 4. Oops, can't quite read that, so I'll make that a little bit better. So there we go. And this is from the region A to B, all right? And this was at 1, and this was at 3. So obviously there's a 2 in here, so we can split this in half. Between these two, there's a 3, so we can split this in half too. Okay, so that gives us 2 this way, 2 that way, and gives us 1, 2, 3, 4. Is the area of the region between f of x and g of x from A to B. And that is what we got, is 4. Now this is a real simple, just a real simple example. But the reason I gave it to you is because I want you to be able just to understand the basic concept before we go any further. Okay?